Triple integrals. Just like when we did the double integral of dx times dy, and we got an area, in a similar fashion, the triple integral of dx times dy times dz will give us a volume. And if we do the triple integral of some function f times dx times dy dz, notice that we get 4 dimensions. So this triple integral would give us the, quote, volume of a 4-dimensional shape. So we're going to do 2 examples. If you understand how to do single integrals and double integrals, there's just more algebraic work. But as usual, the part that throws most people is trying to find the limits. So let's do this example. We want to evaluate the triple integral over r of z times dv, where r is the solid tetrahedron bounded by the coordinate axes and the plane x plus y plus z equals 1. I have drawn a picture of this solid tetrahedron down below. Now, in case you're wondering how I got the front part, this front triangle, this is the plane x plus y plus z equals 0 bounded by the axes. And I did this by starting where I let x and y equal 0, which gave me z equals 1. And then I let x and z equal 0, which gave me y equals 1. And did a similar thing to get x equals 1 over here. And then we just connect those dots. That's the way we generally write, that is, generally draw a plane in 3 dimensions. We draw this triangular part and know extends in all directions, except this won't because we have the other bounds, which are our coordinate axes. Now, if we're to take a look at a thin slice, which I've drawn for you in here, how can I use this to find my bounds? Well, let's start with the z bound. Let's see if we can find the z bound. And I'm not going to substitute in for z here. I'll leave that as z times dv. Well, z starts in the xy plane down here. So we start at z equals 0. And we keep going until we reach the plane where we could write the plane as z equals 1 minus x minus y. So we would go from z equals 0 up to the plane 1 minus x minus y equals z. Now how about the y? Let's do the y next. So if I can do the y second, notice I start at this y and go up to this y. So I start at y equals 0, and then I go to this line. What's the equation of the line? So if I look at the points in the xy plane only, I could easily find the equation of that line, and it ends up being y equals 1 minus x. So I start at y equals 0 and end at y equals 1 minus x. And then I start making these cross sections, if you would, down here at x equals 0, and I stop making them up here at x equals 1. That is from here, 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 and all the way down there. And notice that what we did is we lost a variable every time in our limits. So let's go in and integrate. And then I said we're going to integrate with respect to z first, then y, then x. So let's see how this works. We'll keep the outer 2 integrals, 0 to 1, and then 0 to 1 minus x. Then we integrate z with respect to z. So we get 1/2 z squared from our lower z, 0, to our upper z, 1 minus x minus y. And we'll put the dy dx back in there. I'm going to go ahead and pull this 1/2 all the way to the outside. Keep my outer two integrals. And then I'm going to plug in this upper z value. So we get 1 minus x minus 1 squared. Minus, plug in the lower z value, which is 0, so I don't need to write it. And we have a simpler integral. Now we're down to a double integral, which says we need to integrate with respect to y next. So we have 1/2, so I'm going to leave the outer integral, 0 to 1. And now I need to integrate this with respect to y. So it's very similar to integrating something like 2 minus y squared dy, because the x is going to be held constant. And if I were to integrate this one over here, we would have negative 1/3 times 2 minus y cubed. The extra negative is from the chain out. So if I were to do the actual one here, we would have negative 1/3 and then 1 minus x minus y cubed from 0 to 1 minus x. So we can plug in the upper y value, giving us 1/2 integral 0 to 1 of, and I'll leave the negative 1/3 here for a little bit longer. If I were to plug in my 1 minus x right there for that y, we would get 1 minus x minus quantity 1 minus x, which would be 0. Minus, plugging in 0 for y, we would get 1 minus x cubed. That is 1 minus x minus 0 cubed dx. So let's see if we can simplify all this before we take the antiderivative. I have a negative here, I have a negative right there, so we would end up with positive 1/6, 0 to 1 of 1 minus x cubed, that is 1 minus x quantity cubed dx. And we finally have a pretty simple integral to do. Let's finish it off. We have 1/6, and then the integral of this would be a u sub as well. So we would end up with times negative 1/4, 1 minus x to the 4th from 0 to 1. Again, 1 minus x all to the 4th. So we have negative 1/24 times, plug in x equals 1, giving us 0, minus, plug in x equals 0, giving us 1, and our final answer would be 1/24. One final example. And I already have the picture for us. Let's evaluate the triple integral of the square root of x squared plus z squared dv over R, where R is a region bounded by y equals x squared plus z squared and y equals 4. So this shape down here is the region over which we're going to evaluate the triple integral. So let's break this integral down just a little bit. Let's do a double integral like this, kind of over d, and let's separate out the y one. So we can write it as square root of x squared plus z squared. And then I'm going to have dy. So I know I want to integrate over y first. And the reason I want to do that is because I have information about y's. And then we're left with delta area, dx dz or vice versa. We'll worry about that in just a bit. But notice that we're going to integrate from our lower limit, so the smaller y is this function, which is going to be x squared plus z squared, up to the higher y value, which is going to be 4. So we do the double integral over d of integrating y. It's just 1 dy because the x's and z's are constant. So we have y from x squared plus z squared to 4 of dA. So I'm just getting this first integral out of the way, the inner one. And we have the double integral over d of 4 minus quantity x squared plus z squared dA. Now, how do we find out what this d is? Now, imagine a light over here, as I've done before, shining down directly down the y-axis. The d would be the shadow that our shape casts in the xz plane. So d is going to be the circle x squared plus z squared equals 4. Notice that this top circle is x squared plus z squared equals 4 because y equals y. And the shadow is going to be that exact circle, but now down in the xz plane. So we can use that to get our limits for x's and z's. But let's do something else instead. Because I already know that when I'm doing something circular, that if I want to integrate over a circular region, I want to change this to polars. So I know I'm going to go from 0 to 2, that's my radius, from 0 out to 2. And then my angle is everything, all the way around the circle. So my theta will be 0 to 2 pi. So if I make my replacements over here, I'll do 0 to 2 pi in the outer integral, and 0 to 2 for my r. And notice that this is going to be 4 minus r squared. And then instead of doing dx dz or dz dx, we can do r dr d theta. Now, we're still missing something, right? Because from up top, we have the square root of x squared plus z squared. I'll make a little space so we can see it. Which should have been in my integrand. Square root of x squared plus z squared. Because this part should have been right here as well. X squared plus z squared. Right, when we integrated the y part, that gave us this, but we left this part off. So let's put it back here, and let's add it back here to the end as well. How does that affect us? Not by much, because I know that if x squared plus z squared equals r squared, then this back part, the square root, is simply r itself, right? R is the square root of x squared plus z squared. So my integral becomes 0 to 2 pi, then 0 to 2, of 4 minus r squared times r squared dr d theta. And let's write this out before we actually integrate. We will have 4r squared minus r to the fourth dr d theta. Now, I know I'm going to integrate theta, or d theta, from 0 to 2 pi, so that's already going to be 2 pi. We've done that a bunch of times, or something similar. So it's really going to be 2 pi times the integral from 0 to 2 of 4r squared minus r to the fourth dr, which is going to be 2 pi times 4/3 r cubed minus r to the fifth over 5 from 0 to 2, which will equal 2 pi times, plug in the top limit, we get 4 times 2 cubed, 32, over 3, minus 2 to the fifth, 32, over 5, minus the bottom limit giving us 0. And if we were to work this all out, we would get 128 pi over 15.